So we are going subatomic, trying to figure out, that age-old question, why electrons cling so tightly to the nucleus.
Right.
Now, you would think, right, opposites attract,
Yeah.
like magnets, basic attraction and
Yeah.
all that. But as it turns out, there's a whole lot more going on
Oh, yeah.
in this tiny, tiny world.
Yeah.
So we're going to explore some pretty mind-blowing quantum phenomena today.
Okay.
Things like how electrons can be both particles and waves at the same time,
Right.
and how they kind of occupy these specific zones around the nucleus.
Yeah.
And there's actually a principle that prevents them from just crashing right into the center. Which is something I definitely did not learn in high school physics.
Yeah, it's really fascinating how much complexity there is at this seemingly simple level. You think about an atom, it's like the basic building block of everything.
Yeah.
But then even within that, there's all these forces and all these principles. Right.
That are kind of governing this atomic dance.
Yeah. So let's start with the basics.
Okay.
Just level set everyone,
Yeah.
We all know the nucleus has those positively charged protons.
Right.
And the electrons are negatively charged, so there's definitely that electromagnetic force pulling them together, right?
Absolutely.
Like a magnet attracting a paperclip or something.
Yeah, that electromagnetic force is kind of like this invisible tether
Okay.
that's holding the electrons to the nucleus.
Okay.
But here's where the analogy to planets orbiting the sun kind of breaks down.
Okay.
We often think about electrons orbiting the nucleus like planets around the sun.
Right.
But it's not really like that.
Okay.
Electrons don't orbit in these neat, predictable paths.
Oh.
They exist in these kind of fuzzy regions of space called orbitals.
Okay.
And these orbitals are more like probability clouds.
Probability cloud.
Yeah. So it's not like we can pinpoint exactly where an electron is at any given moment.
Oh. It's more like we know there's a certain probability of finding it within a certain region of space.
Okay, so it's more about where it's most likely to be.
Exactly.
Rather than an exact, fixed path.
Exactly.
So it's kind of like saying it could be anywhere within this cloud, but some locations are more probable than others.
Exactly. Yeah, and to kind of visualize that, you can think of it like trying to pin down the location of a spinning fan blade.
Okay.
You see this glur, but you can't say exactly where the blade is at any given moment.
Yeah, that's a good analogy.
Yeah, so it's kind of similar with electrons.
Okay, so each of these orbitals, though, they each have their own energy level.
Right.
And a certain number of electrons they can hold.
Exactly. And you can think of it like a concert venue.
Okay.
With different tiers of seating.
Yeah.
You've got the floor seats, you've got the balcony.
Right.
And each level can accommodate a certain number of people.
Yeah.
Not everyone can sit in the front row. So similarly, each orbital has a limited capacity for electrons.
Okay. That makes sense. But if we're talking about these different energy levels, does that mean some electrons have more energy than others?
Yeah.
And how does that play into their, relationship with the nucleus?
That's a great question. And you're right, electrons in different orbitals do have different energy levels.
Okay.
And generally, the further an electron is from the nucleus, the higher its energy level.
Okay.
So you can kind of think of it like climbing a ladder.
Okay.
The higher you climb, the more potential energy you gain.
Right.
And so similarly, the further an electron is from the nucleus, the more energy it has.
And the more energy it has, the less tightly it's bound to the nucleus, right?
Exactly.
Yeah.
So it's kind of this balancing act.
So it's like a tug and war then.
Yeah.
Like the electromagnetic force is trying to pull it in,
Right.
but the electron's energy is kind of trying to push it outward.
Exactly.
Oh.
And it's this balancing act that really gives rise to the unique properties of different elements. The number of electrons an atom has and the way they're arranged in these energy levels, that determines how that atom is going to interact with other atoms.
Okay.
How it's going to form bonds and create the molecules that make up everything around us.
So that kind of brings me to something I was thinking about.
Yeah.
Like you said, the number of electrons
Right.
an atom has kind of dictates its chemical properties.
Yeah.
But if they're attracted to the nucleus, why don't they all just pile into the lowest energy level closest to the center?
Right.
Wouldn't that be the most stable arrangement?
That's a great question, and that's where things get really interesting.
Yeah.
Because if they all just piled into the lowest energy level, atoms would collapse.
Oh.
And chemistry as we know it would cease to exist.
Wow.
So there's got to be something else going on, right?
Yeah.
And to answer that question, we need to dive into some of the more mind-bending principles of quantum mechanics.
Okay.
Things like the Pauli exclusion principle
Okay.
and the Heisenberg uncertainty principle.
Okay. Now you've got my attention. Let's unpack some of these quantum mysteries.
All right, let's do it. All right, so let's start with this Pauli exclusion principle.
Okay.
It states that no two electrons in an atom can have the same set of quantum numbers.
Okay.
So remember those numbers we talked about earlier?
Right.
Describing like an electron's energy level, its shape, its orientation in space, and its spin.
Okay.
It's basically like each electron needs its own unique ID card to exist within the atom.
Gotcha.
So even if they're in the same orbital, they can't have the exact same energy and spin.
Okay, so it's like saying they can be in the same, like, seating area,
Right.
but they can't occupy the same exact seat.
That's a great analogy.
Okay.
And, you know, this seemingly simple rule, it has a profound impact on the structure of matter.
Really?
Yeah, it explains why electrons arrange themselves into those different energy levels and orbitals we were talking about.
Okay.
If all the electrons could just pile into the lowest energy level, atoms would collapse in on themselves.
Oh, wow.
And chemistry, as we know it, would cease to exist.
Okay, so this is what's preventing atoms from just imploding.
Exactly.
Wow, that's a pretty big deal.
It is, and it also explains why different elements have unique chemical properties.
Oh, okay.
You know, the arrangement of electrons in their orbitals dictates how those atoms are going to interact with other atoms, how they're going to form bonds, and create the diverse array of molecules that make up our world.
Okay, so the Pauli exclusion principle, that's all about, like, keeping the electrons organized within the atom.
Yeah, you can think of it that way.
Okay, but what about this Heisenberg uncertainty principle? How does that play into all of this?
All right, so the Heisenberg uncertainty principle, this adds another layer of complexity to this atomic dance.
Okay.
And it states that we can't know both the position and the momentum of an electron with perfect accuracy at the same time.
Okay.
So the more precisely we know its location, the less we know about its momentum.
Okay.
And vice versa.
So it's like trying to track a hummingbird or something. If you're focused on its position, you have no idea how fast it's going or what direction.
Right.
And if you're trying to measure its speed, then its position becomes blurry.
Exactly. That's a perfect analogy.
Okay.
And this inherent uncertainty in the quantum world, it has a profound impact on how electrons behave in atoms.
Really?
Yeah. You know, if an electron were to get too close to the nucleus, its position would be very well defined.
Okay.
Meaning its momentum would become incredibly uncertain.
Okay.
It would essentially be moving so erratically that it couldn't stay trapped in the nucleus.
Okay, so the Heisenberg uncertainty principle
Yeah.
is what's like keeping the electrons from spiraling into the nucleus
Exactly.
and causing atomic chaos.
Exactly. It creates this kind of buffer zone,
Great.
preventing electrons from getting too cozy with those protons in the nucleus.
Gotcha. So it's this interplay between this electromagnetic force trying to pull it in
Right.
and the uncertainty principle kind of pushing it out.
Exactly.
That keeps them in these stable orbitals around the nucleus.
Exactly. It's like this delicate balancing act.
So it's like a delicate balancing act between these fundamental forces
Right.
that's happening within every atom
Yeah.
that makes up everything we see and touch. It's pretty mind-boggling.
It is. It's mind-boggling. And these quantum principles, they have far-reaching consequences.
Yeah.
You know, they impact everything from chemical reactions to the behavior of materials.
Really?
Like, for example, even the formation of something as simple as table salt relies on these principles.
Table salt.
Yeah. So sodium wants to lose its outermost electron to achieve a stable configuration.
Okay.
And chlorine is eager to gain one.
Okay.
So when they meet, it's like a perfect match.
Right.
Sodium donates its electron to chlorine.
Yeah.
They both end up with those stable electron arrangements.
Okay.
And that transfer of electrons creates an ionic bond,
Okay.
forming sodium chloride, which is the chemical name for table salt.
Wow.
So this drive for stable electron configurations, it's a fundamental force in chemistry. It drives countless reactions and shapes the molecules that make up our world.
So even something as simple as sprinkling salt on our food
Yeah.
is governed by these complex quantum interactions happening at the atomic level.
Exactly. It really highlights how the microscopic is connected to the macroscopic.
Yeah, it makes you wonder, like, what other everyday phenomena are rooted in this, like, hidden world of quantum mechanics?
Well, almost everything, really, if you think about it.
Oh, wow.
The way materials conduct electricity, the colors we see,
Yeah.
the very functioning of life itself.
Wow.
It all boils down to the behavior of electrons and their interactions with atoms and molecules.
Okay.
For instance, you know, the principles we've been discussing, they're crucial for understanding how semiconductors work.
Semiconductors, those are the materials that power our computers and smartphones, right?
Exactly.
Yeah, I've always wondered how those, like, tiny little chips can do so much.
They really are remarkable.
Yeah.
Semiconductors are materials that have an electrical conductivity that's somewhere between a conductor like copper and an insulator like rubber.
Right.
And their unique properties stem from the way electrons behave within their atomic structure.
So it's all about manipulating these tiny electrons.
Exactly.
But how do we control something so small?
That's where our understanding of quantum mechanics comes in.
Okay.
So by carefully controlling the composition and structure of semiconductor materials, we can fine-tune the energy levels of electrons and create specific pathways for them to flow.
Oh, wow.
And this is how we build transistors, which are the fundamental building blocks of modern electronics.
So transistors are essentially like these tiny little electron traffic controllers.
That's a great way to put it, yeah.
Directing the flow of electrons to create the ones and zeros that make up all the digital information.
Exactly. And the miniaturization of transistors has been a key driver in this exponential growth of computing power.
Right.
We've gone from these room-sized computers to devices that fit in our pockets.
Right.
All thanks to our ability to manipulate electrons at the quantum level.
It's incredible how something so small can have such a huge impact on our lives.
It really is.
But are there any limits to how small we can make these transistors?
That's a great question, and it's a question that researchers are grappling with right now.
Okay.
As we continue to shrink transistors, we're starting to encounter the fundamental limits of quantum mechanics.
Oh, wow.
At extremely small scales, the wave-like nature of electrons becomes more pronounced.
Okay.
And those uncertainty effects we were talking about, they start to play a bigger role.
So they start behaving in unpredictable ways.
Exactly. It becomes harder to control their flow.
Okay.
And that's one of the big challenges facing the future of computing.
Right.
But researchers are exploring new materials and new approaches to overcome these quantum limitations.
Okay.
Like quantum computing, which harnesses the strangeness of the quantum world to perform calculations in entirely new ways.
Quantum computing, that sounds like something straight out of science fiction.
It does.
But it also sounds incredibly exciting.
It is. And it just goes to show you that our deep dive into the world of electrons and atoms, it's not just some theoretical exercise. It has profound implications for our understanding of the universe and for the future of technology.
Absolutely. I feel like I've gained a whole new appreciation for this hidden world of atoms and electrons.
Yeah.
It's amazing to think that all this complexity is happening all around us all the time.
It really is. And we've only just scratched the surface.
Right.
There's so much more to explore in the realm of quantum mechanics. But before we go down that rabbit hole, perhaps we should take a break and let all this information sink in.
Yeah, good idea. Our listeners' brains are probably buzzing with all these quantum wonders.
Yeah, probably.
We'll be back in a moment to continue our deep dive.
Okay.
And explore some even more mind-blowing concepts. Welcome back to the deep dive. We've been on this crazy journey exploring the world of electrons and how they just hang out in atoms.
Yeah, it's really fascinating.
Yeah, so it's pretty incredible to think that these tiny particles, these electrons that are governed by these laws of quantum mechanics, are responsible for all this complexity and diversity in the universe.
Yeah, it's like everything is connected.
Right.
You know, we started by talking about these fundamental forces within a single atom.
Right.
And now we're talking about how those same principles kind of scale up to shape the molecules and materials that make up the entire world.
Right. Yeah, it's like this cosmic domino effect. Like these
so.
Quantum rules we discussed. They're not just abstract concepts, right?
All right.
They actually have tangible consequences that rivel outwards and affect everything, you know, from the air we breathe to the stars in the sky.
Yeah, it's pretty amazing.
So let's talk about covalent bonds for a second.
Okay.
So when two atoms, they're okay, let's share some electrons to get to that stable electron configuration that we were talking about.
Yeah.
It's not just a random sharing.
No, it's very specific.
How they share those electrons is determined by the overlap of their atomic orbitals.
Exactly.
So those orbitals, those probability clouds, they actually merge together.
Yeah, you can think of it like those dance zones blending together to create this bigger dance floor for the electrons.
So the resulting molecular orbitals, that determines the shape and properties of the whole molecule.
Exactly.
Okay, so for example, a water molecule, H2O, it's got that bent shape because of the specific arrangement of those molecular orbitals.
Exactly.
So the shape of a water molecule, something we just take for granted every single day, is dictated by these quantum interactions.
It really is.
Happening at the subatomic level.
It is.
That's pretty amazing.
And that bent shape, it's not just some random quirk, you know?
Right.
It gives water its unique properties as a polar molecule.
Okay.
Meaning it has a slightly positive end and a slightly negative end.
Okay.
And that polarity makes water such a good solvent.
Right, so it can dissolve a bunch of different substances.
Exactly.
So even the simple act of like water dissolving salt or sugar,
Yeah.
it all comes back to these molecular orbitals and the quantum forces that shape them.
It all starts at that fundamental level.
And it's not just like simple molecules like water, right?
Right.
These same principles apply to like way more complex molecules like proteins and DNA.
Absolutely.
All those other crazy molecules that make up like living organisms.
Exactly. So from the tiniest atom to the most complex living being,
Yeah.
it's all connected by these fundamental principles.
That is a really profound thought.
It is. It really highlights the unity of nature.
Right. Like we always try to like separate, you know, physics and chemistry and biology, but they're really all intertwined.
Exactly. At the most fundamental level, they're all connected.
It's like we're peeling back the layers of reality and realizing that everything is like woven together.
So it's all this intricate web of interactions.
And those interactions aren't just happening at the microscopic level, right?
Right. They're responsible for like the macroscopic properties of materials as well.
Oh,
So like the way a material conducts electricity, its strength, its flexibility, it's all influenced by those interactions between atoms and molecules.
So whether we're talking about like a chemical reaction or the properties of some crazy complex material, it all comes back to those quantum rules governing how electrons behave.
It all starts there.
It really is fascinating.
It is. It bridges that gap between the subatomic world and our everyday experiences.
Right.
Showing us that the universe is so much more interconnected and complex than we often realize.
Well, I think it's safe to say our brains are officially full of quantum wonders today.
Yeah, I think so.
We journeyed from like the atomic dance floor all the way to the grand symphony of the universe.
We did.
So we explored all the crazy, intricate ways electrons are held within atoms and how those interactions shape pretty much everything around us.
It's pretty amazing.
We delved into like the weirdness of quantum mechanics and how it affects not only the subatomic realm, but also, you know, the world that we experience every single day.
Exactly.
So it's been an incredible journey.
It has.
And I hope our listeners are leaving with like this newfound appreciation for the beauty and complexity of the universe.
I hope so too.
And it's just this reminder that there's always more to discover, more to learn.
Yeah.
More to ponder about just the nature of reality.
Keep asking questions.
Yeah, and as always, keep exploring.
Let's keep that curiosity alive.
Yeah, because the more we learn about the universe, the more we realize how much more there is to learn.
Absolutely. So until next time, keep diving deep.